We are proving 8 algebraic identities associated with complex numbers. We've already done 1 and 2 in a previous video, so in this video we're going to do identity 3 and 4. I think we'll do 4 first since it's significantly easier. It basically says that if you take the sum of two complex numbers, z1 and z2, and then take the complex conjugate, you'll get the same result as if you take the complex conjugate of both z1 and z2 and then add them together. So here we go. All right, well, as we stated earlier, we can write z1 as, well, let me write it out, z1 plus z2 conjugate. We can write these in the rectangular form, where z1 is x1 plus iy1 plus z2, which is x2 plus iy2. And then we're taking the complex conjugate of that. Well, let's keep the complex conjugate bar, but let's do some rearranging down here. Let's write x1, here's the complex conjugate bar, x1 plus x2 plus iy1 plus iy2. Well, I'm going to factor out the I and just do it this way. Skip a baby step there. Okay, so these are equivalent, and notice that this, under this complex conjugate bar, is a complex number. This is the real part, x1 plus x2 is real, plus I times another real part, y1 plus y2. Okay, so the complex conjugate of that is simply remove the complex conjugate bar and turn this into a minus sign. So we get x1 plus x2 minus I, y1 plus y2. And now I'm going to distribute the I through, or maybe negative I, through these parentheses. So I get, let me go to the right so I don't run out of room, x1 plus x2 minus iy1 minus iy2, which can be written, just reorder it, x1 minus iy1 plus x2 minus iy2. Well, what do we have here? What is that and what is that? z1 is x1 plus iy1, so this is the complex conjugate of x1 plus iy1. That's the complex conjugate of z1. Plus, this is the complex conjugate of x2 plus iy2, which is the complex conjugate of z2. And we've proven number 4, identity number 4. Okay, let's go back to number 3 now. So the video doesn't get too long. I already wrote part of this out. Okay, so identity number 3 is proving that the complex conjugate of the quotient of two complex numbers is equal to the complex conjugate of the first over the complex conjugate of the second. And of course, z2 can't be a 0 because it is in the denominator of the fraction. Okay, so by substituting using this rectangular form, standard form, z1 is x1 plus iy1, z2 is x2 plus iy2, and the complex conjugate bar is over. All we're going to do, I could even put parentheses around these if I wanted to. There are implied parentheses around every numerator and every denominator. So now this looks just like this. Well, I multiplied the numerator and denominator both by the complex conjugate of the denominator, which would be x2 minus iy2. So this is just, as a fraction, this is equal to 1. x2 minus I, y2 over the same. Well, I'm going to keep the denominator the same pretty much until the last step. I'm not going to do anything with it. I want you to notice, though, that the denominator is a real number. Remember, when you multiply a complex number by its complex conjugate, you always get, this would be x2 squared plus y2 squared. Remember, when you FOIL it out, that the outer and inner cancel out and there's no I at all. This is a real number denominator. Okay, well now let's look at the numerator and let's FOIL it out. The first is x1, x2. Now we jump to the last. We're doing it a little bit out of order. Let's go to the L of FOIL. That would be, yes, last times last is going to be, well, certainly y1, y2. And then I times negative I is negative I squared. Negative negative 1 is just 1. So we get y1, y2. Next, we will get, let's see, let's do the inner, which would be I times x2, y1, which is what we have here. I times x2, y1. You'll notice I factored the I out. And then the outer term would give us a negative I x1, y2, which is exactly what this is. I times negative 1, I times a negative x1, y2. So if you distribute this through, you get exactly what we had upstairs here. So this numerator is equivalent to this numerator, just kind of FOILed out, and we factored out the I. Now remember, I mentioned that this denominator is a real number. Well, it should be obvious to see that if I take a complex number of this form, we know the complex conjugate is a minus bi. Well, if I put it over, divided by, say, r, where r is a real number, well, its complex conjugate is simply going to be a minus bi over r. Now, r has to be a real number. It can't be a non-real complex number. But as long as it's a real, these two are complex conjugates. So, I can remove this complex conjugate bar by simply turning this plus into a minus, because after all, we've got a real plus I times real. So this is a complex number written in the standard form. Here's the real part plus I times the complex part, or imaginary part, I should say. So all I need to do is remove this bar and turn that plus into a minus, which I have right here. Let me scan out a bit, give us a little more room to work with. And then on the right, all I did is distribute the negative I through here and here. So we have x1, x2 plus y1, y2, minus I times x2, y1, then positive, because negative times negative, I times x1, y2. So that's all I did in that step. Well, the next step is I'm going to take these four terms and factor them by grouping. Okay, so the first thing I'm going to take out is x2. Let me find the two terms that have an x2 in them. Right there. So if I pull out the x2, I'm going to get x1 minus iy1. x1 minus iy1 plus, now I'm going to, this is the only tricky part of the proof. It'll be simple to verify it, though. I am going to pull out iy2. And you'll see, this will be easy to test in just a minute. I'm going to get this same expression right here. x1 minus iy1. We'll double check that in a minute. Let me write down the denominator. Okay, looks like my pen is running out of ink. Let's verify that these two terms are equivalent to this expression right here. All right, what do I get? Let's look at this distributing through. I would get IY2 times negative IY1. Well, that's just going to be Y1 times Y2, because I times negative I is just 1. I squared is negative 1. Take the opposite of that, you get 1. So that's this term here. And then here we get plus I x1 y2. Okay, well, this is equal to, maybe I'll move to the right. We have two terms in the numerator. They have a common term. Let's factor it out. x1 minus I y1. And what are we left with? x2 plus I y2. Over the same denominator, x2 plus I y2, x2 minus I y2. Which can be simplified very easily. We have x2 plus I y2 upstairs and downstairs, so it cancels. And we get that this is x1 minus I y1 over x2 minus I y2, which is exactly the complex conjugate of z over the complex conjugate of z1 over the complex conjugate of z2, which was exactly what we wanted to prove. We proved that z1 over z2 complex conjugate is equal to complex conjugate of z1 over the complex conjugate of z2.